Hi there. This is the second video for section 2.8. On this video, I'm going to explain how to find the first and second derivative and also where a derivative does not exist. As I mentioned, this is the second part of 2.8. The first part, I covered how to find the derivative and what the derivative is. Just a quick summary, the derivative is a function, which means an equation where you can find the slope of any tangent line at any point x that you plug into the equation. The derivative at a point was the first thing we did, and that is just a specific numerical value of a specific slope at a given point. So the derivative at a point is a number. The derivative in general is a function which gives the derivative at any point that you specify. The way we find a derivative is the same way we found the derivative at a point. We use the difference quotient. So I'll go ahead and show you for this example A. I'm going to demonstrate the derivative of y equals 3x squared. So I'll just use this first formula for the difference quotient. If you're more partial to the other version of the difference quotient, feel free to use that one. They come out the same. I will use this one. And so instead of plugging in a number for x or even plugging in the letter a, as we did previously, we're just going to leave it as x. We're going to leave it as x and say, okay, we're going to actually find the derivative at any point x. And just to recall, we have to simplify this fraction, the numerator of the fraction. So we have x, and we have our function, which was given to us in an equation form as 3x squared. And then we're going to be plugging in the x and x plus h. Those are our two values that we're plugging in to our functions. And plugging in x doesn't change anything, so I get 3x squared. Plugging in x plus h gives me 3 times that input squared. Oops. Squared. That's because of the function right here. The x thing is being squared. And I'm just going to simplify that just a little bit, squaring things out. Make sure to do your distributive properties or foiling or however you learned it so that you have all three terms here and that you multiply according to the order of operations. So you end up with 3 times each of those things. All right, so we're going to put that into this formula. Computing the limit still. F of x plus h was given as 3x squared plus 6xh plus 3h squared. And then fx is 3x squared. And then the denominator is just h. Okay. And then I get the limit as h approaches 0. In the numerator, we have a 3x squared and we have minus 3x squared. Those add to 0. So all I'm left with on the top is 6xh plus 3h divided by h. And we'll need to simplify this. You can't plug in 0 yet because you have 0 in the denominator and 0 in the numerator, which is called indeterminate. So we need to do more investigation. We need to do more algebra in this case. So we can actually substitute values that are very close to 0 and ultimately 0 itself. So we can simplify this using the factoring property, or we can just divide using the distributive property. I did factoring last time, so I'll do distributing this time. Each thing is being divided by h, so I can write each one divided by h. Right, each thing on the top is being divided by h on the bottom, so it looks like that. And now I know that h divided by h is 1 over 1. You know, h divided by h is 1, and dividing or multiplying by 1 does nothing. So all these h's divide out, or as a lot of people like to say, cancel. And I'm left with 6x plus 3. Hold on a second. Hold on. Let me find out where I messed up. All right, I found it. I don't know if you discovered it as well. You're wondering why I did something mistakenly. My error, I knew it wasn't working out the way it's supposed to because I know a little bit more about shortcut rules of finding derivatives. The x plus h plugged into the function gave us a plus 3h squared. And when I wrote it over here, I just said plus 3h. I forgot the square. I think I may have even mentioned like don't make a mistake. So I literally made a mistake there and forgot the square. Okay, so that cascades down here. So this would be a 3h squared. And then I get 3h squared over h. And here, when I divide out, certainly h over h is going to simplify, but I'm still going to be left with an h in the numerator because I have 3h squared on the top and h on the bottom. Okay, so 3h squared over h, one of the h's on the top divides out with one of the h's at the bottom, leaving a 1 and 1. So I'm left with 6x plus 3h. All right. Well, I found my mistake. Math, you make a lot of mistakes in math. That's how we learn. So I am not ashamed of doing that every now and then. Just hope to keep it to a minimum. So now we're going to let this h be infinitesimally close to 0 from either side. And so 3 times the number, which is infinitesimally close to 0, is going to be 0. This gives an answer of 6x plus 0, or in fact, 6x. So we say the derivative of this function is equal to 6x. All right, so that's called the derivative of the function 3x squared. That is the answer to this particular question. All right, so on to example B. Example B, it's a little bit of a repeat thing. It says find the derivative of y equals 3x squared. So what's going on here? Well, I mentioned in the beginning of this video that the derivative is a function. It's an equation. In this case, the derivative is equal to 6x. It could be more complicated. It could be like ln x or 6x cubed plus 2x, or the derivative is a function that's based on the original function that we did using the difference quotient. In this case, it's a pretty simple one. I just made up a simple example. The derivative is an equation equal to 6x. But that is a function. The derivative is a function, as I just am sort of repeating myself. So we can find the derivative of any function. So we can pretend, or even just say, this is a function, and I can find the derivative of this function. So this is going to be sort of our new y equals equation, and we're going to find the derivative of this. So find the derivative of this. And finding the derivative of the derivative function is called the second derivative. So our main objective, one of our two main objectives in this particular video, is to find the second derivative. Second derivative is just derivative of the derivative. Okay, so I'm going to repeat the process I just did, doing my difference quotient. But for the function, I'm going to be using this derivative thing. So we could write using different formulas, like not reusing the letter f, since it kind of refers to this original function. But I think you're understanding what I'm saying. We're going to treat this as our new y equals equation, and we're going to find the derivative of that new equation, and thus find the second derivative. Okay, so now I have x and I have y equals 6x. And I'm going to be still plugging in the values x and x plus h. When I plug in x, I get 6x. When I plug in x plus h, I get 6x plus h, which just simplifies to 6x plus 6h. And then just like before, I'm going to put those things into my formula here. Fx plus h is 6x plus 6h. Fx right here is 6x. And this is divided by h. So I'm just taking these values for x and x plus h and putting them into my difference quotient formula. And then I'll see if I can do some algebra simplification. In this case, I have a positive 6x and a minus 6x. Those add to 0. So I'm left with the limit as x approaches 0 of 6h over h. And these h's will divide out. And that gives me this is h. That gives me the limit as h approaches 0 of just 6. Now, some students get a little bit confused, like, well, what do I do with the h? What's going on here is whatever h's are in this particular equation, we are going to find out when they're infinitesimally close to zero. There are no h's in this equation, so it really doesn't, h being 0 or 7 doesn't really impact the value. The value of this is 6. Just like an equation like y equals 7, it doesn't matter what x is, y is always 7. In this case, it doesn't matter what h is. The answer here for the second derivative is always 6. So this is considered a function, right? The second derivative is written as equal to 6. The notation for the second derivative is a little bit weirder than the notation for the first derivative. I'm going to do it in black over here. The second derivative is written with a little 2 here, d squared y over dx squared, and that's equal to 6. That is how we write the second derivative. Or if you're using the, the little prime notation, you would just say f double prime is equal to 6, or some people just write y double prime is equal to 6. Those are acceptable, just not preferable. And why it's written as d squared y dx squared is a little bit more beyond our current level of calculus, so I can explain it when we do a little bit more of the math. But that's how it's written. So first derivative, difference quotient, get your answer as a function. Second derivative, take the first derivative function, differentiate it using the difference quotient as a function. All right, for the last bit of today, I'm going to point out that derivatives do not always exist. We could say, oh, just find the derivative. So why wouldn't the derivative exist? Well, I want you to refer back to the fact that limits don't always exist. We did a bunch of limits in chapter 2, and sometimes the answer was d and e. It did not exist. And that was primarily because the limit from one side was not the same as the limit from the other side. The limits didn't agree. The two-sided limits didn't agree from one side to this side. There are some other possibilities of do not exist, where you couldn't compute a limit to a function because all the values didn't exist. But generally, you need something very unexpected, like a discontinuity, or something where you get two different answers from two different sides for something like a limit not to exist. And because the derivative is just a limit, then when the limit doesn't exist, then the derivative would not exist. So 3 classical examples of where a derivative does not exist. There are some very small edge cases, but for a Calc 1 student, if you know these 3 examples, you'll know what you need to know about when derivatives don't exist. So the first example I have here, it's labeled a corner. This is actually called a cusp. That's the word for it. Or comes to some sort of point or corner, what they say. So the reason why the derivative doesn't exist here is because if I take the corner point and I take, let me use black, I guess. If I take this corner point and I take a point very close by on the right side, this tangent line has a positive slope. I don't know, positive 2, positive 4, I don't know, something like that. If I get closer, it's going to be a bigger positive number, positive 10 or positive 30. So if I get 2 points really close to each other, I'll get a very large positive slope at that point A. But instead, if starting at that corner point, I take a point to the left, right, on the function, and I connect it to find what the tangent line is approaching, it's a large negative slope. So whatever those slopes are, large positive slope, large negative slope, they are not going to be equal to each other. So we get 2 different answers, 2 different slopes from 2 different sides. So this slope does not exist. Notice the function is continuous and the function exists at A. I mean, there's definitely a point there. I can see it, right? But just because a point exists doesn't mean that the slope or the derivative does not exist. So the derivative does not exist because the slope doesn't exist at that point. When we have a discontinuity, even though we may have the same limit from the left and the right, we have a discontinuity. That's going to give us a non-computable slope or derivative at that point, because we only have a point from the right-hand side. From the left-hand side, we have a different set of points. And the last example of where you have a function that will not have a derivative is when you have a vertical tangent line. So right here, at this point A, you get something like, positive or negative infinity, depending on which direction you come from in terms of the slope at that point. Again, can't really have those two different answers, and plus or minus infinity would be a good description, but at this level, not really acceptable. So you would just say, okay, the derivative does not exist at that point A because we have this problem with infinities at that point. All right, so those are the classic three examples of functions where the derivative does not exist, at least at some points on those functions. It may exist at other points, but not at all points, certainly the ones A in each of those three examples. All right, so in today's video, I tried to do a couple of things. I tried to show you how to find the second derivative, and I also attempted to show you where or how a function actually can't have a derivative at all points. It definitely could have a situation where it only has a derivative at some places, and in general, there wouldn't be one derivative function that could give us the derivative at any point x. So that's the end of this video. Hopefully it was useful. Hopefully you found it interesting, and always reach out if you have any questions or need any additional help with any of the stuff. Okay, awesome. Have a good day or evening, however this finds you.